All right, we're continuing with polar functions, and now we're going to find the area inside the polar regions because all of these things are enclosed, so we can find the area inside of them. So let's say, for example, I asked you to find the area of a circle. We know the area is pi r squared, whatever r is. And let's just say r is 1 in these cases. It would just be pi. So how can we turn this into a formula where, let's say, for example, I wanted to find the area of a piece of this instead, from like, let's say, to 0 to pi over 6. Well, there's a formula for this. It's called the area of a sector formula. Without going into too much where it comes from, to find the area of any sector, all you do is 1/2 theta r squared. And all you need to do is plug in what theta is. So if you wanted to find from 0 to pi over 6, you would just plug in pi over 6 to that. So 1/2 pi over 6 r squared. And then if r is 1, that would be pi over 12. So the area of this section right here would be pi over 12 in this case, which should make sense because this is 1, basically, if I were to chop this up. We just said that the entire area is pi, and there's a radius of 1. So this is essentially 1/12 of it. So pi over 12 is logical. Anyway, we are going to now do this with all of our crazy polar functions. And let's back up and think about one of the most basic graphs, the circle, but let's actually graph it and talk about the polar function equation. Let's do r equals 1, which is a circle with radius 1. So in polar land, remember, we graph according to a radius. For every angle you plug in, you get that radius. In this case, it's just 1. Beautiful. Now, in our old language of accumulation to find area under the curve, to find the area under any function, you graph the function, let's call it f, and you take the integral from your start point A to your stop point B, A to B, area under the curve, and it's pretty basic. And what it does is this is the important part, so don't miss this. You're adding up a bunch of rectangles that are infinitely skinny all side by side. That's what this calculation does. It adds up infinitely skinny, infinitely many rectangles. So, can we apply a similar idea to the world of polar functions? And yes, of course we can. And it works like this. Let's say I wanted to find the area inside of this polar region. So I want to find all of the area inside the circle. Well, the way polar functions work is if you plug in 0, you would get this value, kind of this radius of 1. If you plugged in pi over 6, you would get this kind of ray. Think about it as a ray that emanates from the center. If you plug in pi over 3, you would get this. So when we do polar areas, here's how it works. You are going to think about it like you are adding up a bunch of infinitely skinny, infinitely many sectors, all emanating from the origin, aka 0, 0. And you want to capture all of this area from this start point, and in this case, to this stop point. So you're going to use an integral. You're going to use this formula. So there's a 1/2. We can put it in front. There's an r squared. And all you have to do, the only thing that's different from this formula up here to how we're going to use it in this class, is you're going to tell it what angle you want to start at, so 0, and what angle you want to stop at. So we want to go all the way around, ending at 2 pi. And then we accumulate, and remember, theta is the variable. When we get to the more complicated examples, obviously r will have, it's a function of theta, what we saw last class. And that's it. So in this case, you do 1/2, 0 to 2 pi. And then r squared, r in this problem was 1, so it's just 1 d theta. So if we pull up Desmos and accumulate this and let Desmos do our calculations, we're going to use Desmos for this until I show you how to do it on the calculator. But it's 1/2 integral, dang it, 1/2 0 to 2 pi. We're just accumulating 1 d theta or dx. It actually doesn't matter what language you use here. And we got pi. So the area of the circle really is pi. So just like the previous one, if I wanted to find the area of the sector, you would do pi over 6. And I think that is the same as pi over 12. So the hardest part of this whole thing is capturing the area you want to actually capture. So this next example is going to be incredibly important. So we are going to find the area inside this guy. I'm going to graph it for you. R equals sine 3 theta. How do we find the area inside this polar region? All right. This one is really, really going to hit the idea hard. So pay attention to this. So the graph is R equals, I'm going to do 2 examples. This is the first, and I'm going to show you a variety of ways how this works. So this first one is R equals sine 3 theta. And usually the phrasing will be something like this. Find the area inside 1 petal, in this case, because you can think of it as a flower. So I want to find the area inside a single petal. All right, so where do we begin? Well, remember, the way this works is all of these sectors emanate from 0, 0. So if you're confused on how the graph is being drawn, go back to Desmos and play around with the bounds. You're going to hear me say this quite a bit. If I plug in pi over 6, let's say, here's where the graph is at pi over 6. Let's go even smaller. How about pi over 12? How about pi over 18? You can see that every time I get smaller, the graph kind of goes like starting here. And then as I make, well, it's 22. As I make the theta value bigger, you start to get the graph. Actually, let's try this. If I make this k, and I say k equals, I don't know, pi over 6. I had a slider for it. No, I wanted to. Anyway, the point is, here's what's happening when you are graphing it. You're starting here, and then as you increase theta, the graph continues around this way. So how do you find the area of this petal? Well, you got to figure out how the sectors kind of work in this problem. And here's what they do. I'm going to zoom way in. If we were to set up our equation, which is area equals 1/2 accumulation, R is just sine of 3 theta, so it's just going to be sine of 3 theta squared d theta. But the tricky part is the bounds. We're starting at 0. And let's say you only wanted to, well, we want to get the entire petal. Here's how the rays kind of emanate from the center. Here's how the sectors work. As you start accumulating, you're adding up these sectors. So this is the area you are accumulating, and it works just like this. You are capturing area in this manner. They're not top down. It's not like rectangles. It is infinitely skinny sectors that all emanate from 0, 0. So the question is, when does it stop doing that? How do you stop it at this area you want? Well, you go back to Desmos, you look at the bounds, and you think, okay, well, let's try pi over 3 again real quick. Oh, that was the answer. Let's try pi over 4. You see how you didn't complete the loop yet? You've got to find the theta value that completes the loop. If you go to pi over 2, look, that's too far. You moved on, and now you would be including like sectors that emanate down in this direction. So it looked like pi over 3 was the answer we were looking for. So in this case, it's as simple as making your top bound pi over 3, and boom. That is going to give you your accumulation that you are after. So 1/2 integral 0 pi over 3, and then r squared squared d theta. Make sure you use d theta because these are functions of theta. That's what I was talking about in the previous problem. See how theta is the variable inside of r? It's just like x is the variable inside of the y function. Same idea. All right, so that's how this is going to work. Now, here's where some other things can come in. Let's say you wanted to find the area of the entire thing, so all 3 petals. Well, obviously, you can multiply this answer by 3, and that would give you all the areas because there's a lot of symmetry here. All 3 of these are the same size. If something looks symmetrical in this language, it is, just FYI. But could you have gotten the area without multiplying by 3 and just kept your bound continuing on? Yeah. So instead, you could have gone from 0 and you could have saw where the shape finishes. So remember, we tried, let's go back here. We tried pi over 2, and that gave me here. What about pi over 3 pi over 2? Well, it's finished. So the question is it now starting to overlap itself, which is something we're going to have to talk about in the next example. If we just go to pi over 2, we're not there. What if we go to some of the other values on the unit circle? So we saw that it finished its first loop at pi over 3. What if I tried something like just pi? Look at that. You see how it already completed its cycle? Let's try going to 5 pi over 6 and see if it also overlaps itself. Look, here's the key. The graph did not complete and fill itself, like meet back to center at 5 pi over 6. So my guess is it's done at pi, and it looks like it is. The problem is if you mess up and go to 2 pi, watch. The graph doesn't change, it just starts overlapping itself. And if you make this bound 2 pi, you're going to get double the answer you want because this thing really is supposed to end at pi. So in other words, watch how I do this. From 0 to pi, here's what your graph does. It goes, it starts accumulating all this area. And then it comes down here because that's what the graph showed me when I was playing with the bounds. And then it keeps going. And then it starts coming up here. Oops, it's really bad. Let's make it nicer. It starts accumulating all of this. And then by pi, it's back to the center again. If you keep going and make the bound 2 pi, you're going to start doing the same area you've already got, and you're going to get double the answer you want. So that's the hardest part, is getting these bounds correct. So in this case, it really was 0 to pi, and that's the thing you're going to hear me say a lot. You have to just test your bounds when you're playing on the, or when you're doing this with your calculator. So when we go to pi, bam, we got 0.785. Which was the same answer we got if we multiplied the previous answer by 3. So remember, the previous answer was pi over 3. Multiply this by 3, same answer. So symmetry is a big part of how this is going to work. And these take practice. Just like the first time I learned volume by rotation, the more of these you do, the more they start to make sense. So we're going to do one more example. And I'm going to do it a variety of ways. So we're going to graph the following. I'm going to do r equals 3 sine theta like this, and r equals 1. So now I have a combination of things. All right, so cool. Here's how the phrasing is going to work. Ready? So remember, this one was r equals 3 sine theta. We can call that r1. We can call this r2, which is just 1. All right, I can ask you tons of different questions with this setup. I can ask you our first question. Let's find the area. So part 1, I want to find the area inside R1, but outside R2. What does that mean? here's what it means. It's this area inside of the red, but not including the area inside the blue. So that would be all of this. So this is the area I want to find. Okay. So how do we do this? Well, first thing, it's going to be kind of a subtraction of two areas. So let's start by finding the entire area inside the red, and then we can subtract out the area inside of the blue. That's how we're going to go about it. Okay. I just want to make sure. Don't want to start with this one. Actually, we'll come back to this one because we want to find something else first. So we're going to come back because there's another question we're going to have to use to do this one. The other question we can do is find the common interior. So let's find the common interior area, which would be, in this case, the area inside both, which is all of this. All right. This is one that's going to be crucial for the next one, because then if I do this one first, I can just subtract it out from the area inside the red and I'm done. That's why I think it's better to do this one first. All right, so the common interior, how are we supposed to do this? Well, remember, we're trying to capture sectors. So to get the common interior, I would like to start by adding up all of this area that starts from 0, 0 and goes all the way along and actually stops right there at this point. So how do I capture this first blue slice right here? Well, notice what curve I'm going out to. All of these sectors went out to the red curve. So this deals with R1 squared d theta 1/2. That's the easy part. The hardest part is the bounds. So we come back to Desmos and we look at this graph, r equals sine theta, 3 sine theta, and we just look at the bounds on it. So from 0 to, let's start at just pi over 6. And you see how it overshot. I wanted to stop it here. So if I went all the way to pi over 6, we'd be capturing all this extra area that I don't want to capture. So let's back it down to pi over 12. We're not there yet. You see how we didn't get to that intersection point? So I don't mind you just practicing with Desmos to find that intersection point. It's probably pi over 9. Not the one a little past. How about pi over 8? Nope, let's make it 9.5. So the idea is we got to find that intersection point. This is kind of a bad example. There's a way to find it, but I'd rather give an example where it's a nice value. Let's try this. Let's make it pi over 2 sine theta. 8, 7, 6 is going to be it. Yeah. All right. I'm going to change the example a little bit. Let's just say that this is 2 sine theta instead, because I want to do a nice one that has a nice bound. I'm never going to give you ones that don't have nice intersection points. So now we're doing 2 sine theta. That way we can actually have a nice intersection point. And that means this would be from 0 to pi over, what was it, 6? From 0 to pi over 6. Okay. That's going to give me this blue area. Then I want to get this other section. So to that, I'm going to add the area from here. And I'm going to start with this sector. And now look, I'm going to the blue curve. And I want to capture all of this area. I want to capture all of this area. And actually, I'm going to do something kind of unique. I'm going to stop it right there. So how do I get this area? Well, again, this part's not the hard part. 1/2 d theta bounds, and then just pay attention to what curve we're using now. These sectors are all going to the blue curve, which is R2. And where did we start it? Well, we started it at pi over 6, the intersection point. And where did we stop it? You go back to Desmos, and you look at where this one stopped. So in this case, this is r equals 1. And we can tell it with circles, you can't play with this like Desmos can with the previous one. But if you remember, this is just like the unit circle. So this basically stopped at pi over 2. So this one on from the area from pi over 6, and I want to stop it at pi over 2. So from pi over 6 to pi over 2. Add them up, and that will give me half of the answer I want, which is all of this. So the question is, can you use symmetry to get the entire thing? Well, hopefully you realize that, yeah, once you have your answer, you can just multiply it by 2. And that will give you the common interior. Okay. So I guess long story short, and I know that was a little clunky, you have to just practice changing the bounds to capture the area you want, and always draw your rays coming out from the center and going to whatever curve you are accumulating. Okay. So now that we have the common interior, I can go back to the first question, find the area inside R1, but outside of R2. Well, to do that, we can just, whatever this answer is, let's say that this answer was A. I can do this area from here all the way around the circle. Oops. And then I can just subtract my answer from the previous part. So let's go back to Desmos. In this case, when does this thing finish? Let's try pi over 2. Well, that only gave me half. I want to go all the way around. Or we could stop here and just multiply that answer by 2. But at this point, it's not too hard to just go all the way. So it looks like it completes itself at pi. If you're not convinced, you can try doing something like 3 pi over 4, just to make sure you didn't overlap yourself. So 3 pi over 4 doesn't get me all the way there. So yes, it looks like pi will get me all the way there. Which means you are accumulating area from, again, 1/2, 0 to pi. That was R1 squared d theta. Take this answer, subtract A, and that will give you the area inside of R1 but outside of R2. All right, we could do similar stuff to find the area of this piece down here. I'm not going to do that. These take a lot of practice, so try your best on the homework. We will go over the homework, and FRQs typically have you finding area inside of these. I will show you how to do it with the calculator on Wednesday, but start at least getting the setups down and then having questions about how to find the bounds, and we will work on that. All right, that's it for now.